So the first question is this one over here. This is a pretty straightforward one. So I'm going to give you a population that has 36 big A, 48 big A little a, and 16 little a. I want you to go and find the allele frequencies, the genotype frequencies, and then answer the question whether this population is in Hardy-Weinberg equilibrium. So go ahead and pause the video now, try to solve it on your own, and then we'll walk through it once you either figured out an answer or got stuck. So go do it yourself and see you back here in a couple of minutes. Okay, so hopefully you pause the video and actually try to do that yourself. I really suggest you do. But let's go through the actual problem itself. Okay, so this is what I like to consider to be a forward problem, where you're given some kind of a population with the number of individuals, so you have to figure out whether this population is in Hardy-Weinberg or not, and in order to do that, you have to look at you have to do the calculations and basically look at the results and whether they correlate with the original or not. So let's look at this. So the population is 36 big A, 48 big A, and 16 little a. Let's first find the allele or gene frequencies, as I mentioned over here. So the total number of individuals is 100, and each individual has 2 alleles. So the total number of alleles is 200. Think about that for 1 second. You have 100 individuals total. Each individual has 2 alleles, so the total number of alleles is 200. Keep that in mind. Next, let's look at the allele or gene frequencies. So we have 2 different alleles available, big A and little a. Big A can be solved by doing this. Little a can be solved by doing this. So let's walk through it. First of all, we have big A. Big A, there are 36 big A, which means that there's 36 big A and 36 big A. Think about that for 1 second. You have 36 individuals with the genotype big A. So in total, you have to add 36 plus another 36. Hopefully that makes sense, because you have 36 individuals with big A. In total, that means that there are 36 individuals with big A, 36 individuals with big A, so you have to add those two together. In addition, you have 48 individuals that are big A, little a. So in this population, the heterozygotes, only 48 big A's. So you're looking for the number of big A's in these populations. And you have big A, little a. This is 36, big A. This is 48, big A, little a. 48 big A over here, 36 big A, 36 big A, and this is what you get. And it's out of a total of 200 alleles. So solving that, you get 0.6. So your A, the frequency of your A allele is 0.6. This also means that the frequency of P, so P, remember, is big A, is 0.6. The same thing happens for little a. You have 16 little a, and then 48 big A, little a. How many little a's are there in total? Remember, 16 individuals have 2 little a alleles. That means in total, you have 16 plus another 16. And then you have to account for these little a's over here, where there are 48 big A, little a's. But 48 individuals have half of their genotype being big A and half of their genotype being little a. So in total, there's also 48 little a's over here that you have to account for. Think about that for a second. This is arguably the most tricky part for a lot of students. So in total, the number of little a alleles within this population is 16 plus another 16 plus 48. And you divide that by 200, and that's 0.4. I think that makes sense. So again, little a correlates to Q, and Q equals 0.4. And you can actually do this. The quick method is if you figure out your p-value and you know that p plus q equals 1, then you know that if you have 0.6 for p, then you know that q is obviously 0.4. So we know that the frequency of A is 0.6, and we know that the frequency of this little a over here is 0.4. So these are your allele or gene frequencies. Okay. The next step is to find the genotype frequencies. The genotype frequencies are using your p squared, q squared, and 2pq formulas. So remember that Q, or excuse me, let's start with P. P correlates to big A. You have big A, that's basically P times P, or P squared, which is 0.6 times 0.6, or 0.6 squared, and that's 0.36. You also have big A, little a. Those are your heterozygotes. Remember that heterozygotes is the individual's big A, little a, and that's found by 2pq. So you use 2pq for big A, little a, 2 times 0.6 times 0.4, that's 0.48. This is the frequency of the big A, little a genotype. Finally, you have little a, which of course correlates to q squared. Q squared is 0.4 squared, and that's 0.16. So these over here are your genotype frequencies after Hardy-Weinberg. So the question, of course, is that you have these frequencies over here, which just so happens in this case to be the same as the original. So that means that this is a situation where the final expected values match the original values perfectly, so it is in Hardy-Weinberg equilibrium. So that's a lot to take in. Go through this question again if you got it incorrectly. If you got it right, good job. But if you didn't get it right, that's okay. Think about it and try to understand the reasoning behind why this is the case. Cool?